Okay. Thank you very much for the introduction, and hi, everybody. Thank you for being here and listening to me. I hope it's not too late and I don't put you to sleep. I try to be entertaining a little bit. So as she mentioned, Dfinity is a cloud computing research lab, and we are creating the next generation protocol for cloud computing that any service provider can join and use this protocol, and then with themselves and jointly, they can provide the cloud service without relying on one specific third party to organize them. So it's like ISPs these days. As part of the cloud computing background, the best way is to talk about agreement, because like in cloud computing, the most important thing is that the servers stay in agreement. And today I'm talking about agreement because agreement is what really we need. So the problem of how to reach agreement when a few of the servers or nodes are faulty started with a fictional war. It's a Game of Thrones type war that three generals wants to invade a city, and they can only win if they invade together, and they lose if they don't invade together. But the problem is one of these generals is adversarial. So he tries his best to make sure they cannot agree on the same time or on the same day. And this is the problem of Byzantine generals that is introduced in 1982. So to formalize the problem, we have n nodes that each start with some input value. And T of our nodes are dishonest and controlled by an adversary. So we define agreement as like all honest nodes output the same bit or the same as the same input value. And we define validity if the bit equals as one of the input bits of an honest node. So it should be an honest input. And we define termination as like each honest party must eventually decide on B. And if one honest party decides on B, all other honest parties should decide on B. So this is a very well-defined problem in distributed computing, and a lot of research happened on them. What we want really is that we want provable security for this specific problem. So we want to provide a protocol that's provably secure for safety and liveness. Safety means that everybody agrees, and liveness means that everybody eventually agrees. So it's like the protocol proceeds. And then another criteria that's recently added to this protocol is that we want something fast and scalable. Scalable in the number of nodes that can run this protocol together. So a very well-known technique for Byzantine agreement protocol is a PBFT-based protocols. In a PBFT-based protocol, the high-level way of solving this problem is that you first choose a leader. Then the leader proposes a message or proposes an input. And then all people who are participating in the protocol, all the servers or nodes, check if the leader sends the same message to everybody and they reach agreement. So it's a very expensive check because everybody should send what they receive from the leader to everybody else. So it's a O of n squared check. And then if they terminate, they agree. If they don't terminate, they have to change the view, change the leader, and repeat. And this is another very expensive procedure because they have to agree on now who is the next leader. So it is interesting that most of the traditional BFT-based protocols didn't really improve it that much. So they can improve to 30 number of servers or up to 100 number of servers, but they couldn't reach agreement among more than that in a practical setting. So now, later on, after a long time after like PBFT-style protocols, blockchain came to the life. So what is blockchain? Blockchain is in a theoretical sense, there are a lot of different definitions of blockchain. What I saw blockchain as is an augmentable data structure. Blockchain is nothing more than a data structure. So it's a data structure that's composed of blocks. It's first look like a tree. Everybody can add a block to this tree. And then the data structure is in a way that it is created and maintained in a distributed setting. So if you have 100 nodes, each node can add to this tree. And the goal is to reach agreement on one of the leaf of the tree. So now if you reach agreement on one of the leaves, it means you reach agreement on the whole path. So then you can amortize the cost. Yeah, that's very simple of how you can use blockchain to reach agreement faster. So now let's compare PBFD-based protocol with blockchain-based protocol. So essentially, blockchain is also a Byzantine agreement protocol. So I'm just using the word chain-based protocol or blockchain-based protocol. And for instance, we can consider a simple Bitcoin protocol. So in PBFD-based, as we said, we first choose a leader. In blockchain, we first choose a block maker. Then leader should propose a message here, proposer propose a block. Nothing different so far. So then in the PBFD-based, we said they have to reach agreement. They have to check if they reach agreement. In blockchain, everybody who received the block just update the chain. They don't check if they reach agreement or not. They are just optimistic. And then in the PBFD-based protocols, they have termination guarantees. So they terminate after they reach agreement. But in blockchain-type protocols, there is no termination. You should always continue working. If you stop working, then the protocol cannot satisfy safety anymore. So it's always working. There is no termination. You continue adding the next block. So, and then you repeat. So if you look at it very carefully, blockchain reduces the cost in two very important costly part of the PBFD-based protocols. First, you never check if you reach agreement, so you don't have that O of n squared cost. And then you never, you kind of repeat always and choose another leader, no matter if the leader is honest or not. So you don't have the cost of view change as well. That's why they are very efficient and scalable. So the key observation we have here until so far is that blockchain is a series of potential agreements because we never check if we reach agreement or not. We just hope that we reach agreement. And then we can amortize the cost and agree once in a while. How we can agree once in a while? With the hope that, OK, we are choosing the leader randomly, so one of these leaders are honest. He proposed the same value to everybody. We agree on the leaf. Then we agree on the whole path. And we amortize the cost. So this is an optimistic protocol. And because at least 2/3 or half of the nodes are honest in different settings, in the synchronous setting, half of the nodes, in the asynchronous setting, 2/3 of the nodes.
Everyone was dishonest. Does this fail?
I'm going to talk about what happens if everyone is dishonest. So you cannot have agreement if everyone is dishonest, no matter in PBFD or in blockchain. So I'm going to talk about lower bounds. So now let's see what is the trade-off. So I talked about the benefits of blockchain, but you can never win something without losing something. So what we lose, really? So PBFD-style protocols give us instant finality. If I agree on something, I instantly know exactly, oh, I agree on this specific thing. So because I checked my agreement. But in blockchain-type protocols, there is no instant finality. It's a probabilistic finality because you don't know if the leader is honest or not. You just hope the leader is honest. And then you wait for some rounds until you reach a point that you, in your mind or in your security setting, that is enough rounds that you are sure at least one of the leaders in the previous rounds are honest. And then you can say, oh, probabilistically, with probability 2/3 to the number of rounds, I reached one honest leader, and then I reached agreement. So Another difference is that PBFT protocols are expensive, so they cannot scale to large number of nodes. But as we said, blockchain protocols are cheaper. They can scale to 5,000 number of nodes or 10,000 number of nodes and even more. So it's like now we are in the path of scalability. So we can scale to larger number of servers, larger number of nodes. So now to answer your question is like, OK, so we know what is Byzantine agreement. We know two methods to achieve it. What is possible and what is not possible in this environment? So there is a lot of interesting research on what is possible and what is not possible. The first interesting result is the FLP result. The FLP result says that no deterministic protocol is possible even if the number of dishonest parties is 0. So even if I have no dishonest parties, it's just crash failure. If my protocol is completely deterministic, I cannot reach agreement. Then there is another interesting impossibility result by Broca and Tong. And they said n is the number of total number of servers or nodes who wants to reach agreement. And remember, f was the number of dishonest nodes or adversarial nodes. So n should be larger than 3f in the asynchronous setting. So if n is smaller than 3f, you cannot reach agreement ever. And there is an impossibility result for that. So yes, if everybody is dishonest, you cannot reach agreement. So then the result of Broca and Tong was a theoretical result. There wasn't any actual protocol. PBFT make it practical and make it actual protocol. And then they said, OK, we kind of need synchrony for liveness. We can reach agreement and have safety if n is larger than 3f. But without synchrony, they couldn't achieve liveness. They couldn't show that the protocol terminates. So they add synchrony to the protocol. And then on the other spectrum, we had blockchains, which has a different assumption. They assume synchrony for safety and liveness. And then with this specific new assumption, they can break the Broca and Tong impossibility result. And they showed that if n is larger than 2f, you can reach agreement.
What kind of error bars are they talking about in probabilistic? Because I assume that having a bigger n would reduce the probability of it being wrong. So what
Yes.
What kind of, is it like 5% error? Or?
No, it depends on the number of rounds that you wait. It's like, for example, if you say I wait 100 rounds for the blockchain to look at the previous 100 rounds, then the probability of you reach agreement is around 2/3 to the 100. Because every time you run the protocol, every round of the protocol, you choose the leader with a probability of around 2/2 or 1/2 based on synchrony or asynchrony assumption. And the leader is good, and then the probability that it helps you to reach agreement is 1/2. Then after so many rounds, you can reach agreement. So the probability is not dependent to the number of nodes. It depends to the number of rounds. OK. So now between PBFT and blockchain type protocols, there is a space that is empty. So the space is that can we have the goods of both worlds? Can we have instant finality? Or at least as soon as we have the agreement, we know that we have the agreement. And also work for large number of parties, work for large number of nodes and scale. So this is Dfinity. So in Dfinity, we can tolerate n larger than 3f plus epsilon. I will define what is epsilon later. And then we assume, similar to PBFT, we assume synchrony for liveness. But the difference between Dfinity and PBFT is that Dfinity scales like blockchain scales to large number of nodes. But at the same time, as soon as we reach agreement, we know that we reached agreement. So it's like it doesn't have exact instant finality, but it has something in between. You are aware of your agreement. In blockchain protocols, you are not aware of your agreement. That's why it's probabilistic. OK. So what is the fundamental steps in Dfinity that we can have these guarantees? What we really do? So the first fundamental step is to choose a leader. And as I described, to choose a leader, one way is to choose it in a round-robin way, but it's not the best way because the adversary can like put all his dishonest nodes at first, and you have to repeat a lot of time to reach agreement. The best way to have a good leader is to choose him randomly. And to choose a leader randomly, we need to create a randomness. And in distributed computing, creating a randomness in a distributed setting is a difficult problem. So now, let's see how PBFT styles usually don't create randomness. They do in a round-robin way. So let's see how blockchain works. So traditional blockchain like Bitcoin and Ethereum, they use proof of work to create randomness. And what is proof of work is that they start with a puzzle. Everybody starts to do some computation on the puzzle, which is a random computation. And who ends the computation in a specific boundary can send his result, and he's the winner. And then he is the next leader. So, but proof of work is not a good way of creating randomness. It's a one way, but it's not a good way. Why? Proof of work is inherently very expensive. Why it is expensive is because, for example, Bitcoin and blockchain protocols need electricity of a European country. I think now it's like Denmark, around Denmark. Us, OK. It's getting larger and larger, I believe. To do the proof of work, it's inherently very, very expensive protocol. And as so, it cannot scale, because as soon as you add more nodes to the system, you add more nodes to the system, you need more power. And then suddenly you need all power in the universe, and you cannot do it anymore. And even if we solve the electricity problem some way, proof of work is fundamentally has limited throughput. Why it has limited throughput? Because we said that proof of work or chain-based protocols should be synchronous. And why it is synchronous? Because every time in each step, you have to solve a proof of work to create a randomness to choose the next leader. And the solution to the proof of work should be fundamentally much, much longer than the network delay. If it's smaller than the network delay, you don't know if the proposer doesn't solve the proof of work or if the message is stuck in the network. So it should be order of magnitude longer than the network delay. So for example, if the network delay is 300 milliseconds, then the solution to the proof of work should be around 10 order of magnitude larger, around seconds. So 3 seconds, 5 seconds, 30 seconds. Currently, they sometimes put it in minutes. So they wait around 10 minutes for each round. So then inherently, every time you can reach agreement is 10 minutes later. So then you cannot have a very high throughput, because as soon as you have larger blocks, your latency in the network goes up. And then you have to have larger proof of work. So inherently, it cannot reach a high throughput system. As a result, for example, Bitcoin has a system that scales to 5,000 nodes, but its throughput is 7 transactions per second. And you can move it to 70 transactions per second, but that's it. You cannot move it further. Theoretically, you cannot move it further. So now we don't want to use blockchain. What we can do? We can derive randomness from a chain itself. We can assume the inputs of the users has some entropy, they are random, and then you can derive randomness from the previous inputs. Why it is not good? First, the inputs doesn't have a lot of entropy. No, they are not random. They usually are very fixed inputs. They are transactions. They don't have that much entropy. Second, assume everybody, this method assumes everybody agreed on the chain before moving to the next round, but we know it's not the case. So if your previous leader is bad, people have different input, then they have different randomness, then they should agree, they fork. Then they have to go back and see, oh, well, now what happens? And it's making the protocol very complicated, so it's not a good way. So another way is that, let's say at each block, we generate a new randomness. There are ways that in distributed computing that you can generate a new randomness. So One way is that each person creates a randomness and then they send it to each other and XOR it with each other. But this problem has a last actor bias. Why? Because if I'm the last actor who is responsible to creating my own randomness and XOR it to the rest of the world, then I can look at the randomness. If it's not in my favor, I can just ignore creating my own randomness and move forward. So I can bias the randomness, and they call it a last actor bias. So, and any fallback mechanism, we can say, oh, if the last actor doesn't produce the randomness, run it again without the last actor. But still, it has a fallback. It introduced a bias to the randomness. It cannot produce a non-biased random value. So there are some protocols that use this way, but they are not good protocols. So now it looks that we are doomed. There is no good way of creating randomness, but there is some good way. So in cryptography, there is a way that we can create randomness. And one way is use the threshold crypto group. What is a threshold group? A threshold group is a group that if k out of n members have to act, then they are necessary to act. And if k out of n members are sufficient to act, they can do something together. Let's do an example for encryption. For example, I can have k out of an encryption group that if k of my members encrypt the message together and participate in the encryption, the k is enough and sufficient. And the k is necessary to encrypt the message. They have to be at least k members, and they are enough to encrypt the message. Another interesting group, threshold groups are threshold signatures. In a group signature, we want to sign a message together. So each person signs with its own signature, then they aggregate the signatures, and as a whole, a group can sign a message. So in a k out of n signature, group signature, is that k people are enough to sign a message together, and and they have to be k people to sign it. And threshold crypto is good to remove the last actor bias. Why they can remove the last actor bias? Because if I created my randomness in a k out of n way, I don't have any last actor, because k can be much smaller than n, and then anybody from this n minus k the rest of the people can be the last actor, and you don't know if you are a last actor or not. So there is no last actor bias anymore. So at least we find one way in cryptography. But the problem with threshold crypto is that it's very expensive. So then it's like if you want to use this type of cryptography at each round of the protocol, you are going to have a very expensive protocol. And the whole point was to make the protocol not expensive. So the whole point is to make sure the protocol is not expensive, and we lose the hope. So, but the important part of the work that we understand is that we can reuse the randomness. We don't need a fresh randomness at every step. We can create one randomness at the start and then sign on it, sign on it, sign on it again, and reuse the randomness. And this way, because we can reuse it, it's not that expensive anymore. So we call this second fundamental step that we did at Dfinity. So we call it consensus without consensus. Why it is consensus? Because we have to agree on the randomness. Why it is without consensus? Because we are creating a pseudo-random function. We don't really create the randomness again. We just create a way to reveal a new value which look like random in the eyes of the adversary. OK, so how we can do that? They usually call this function verifiable random functions, because you can create this new next random value, and it's verifiable because everybody can check if it's the correct next random value or not. And then you agree once, then you agree always. So at Dfinity, we use BLS threshold signature to do this process of using the randomness, creating the randomness. First, we do a distributed key generation to create the first group to like set up the group, because we need to have a k out of n threshold group, and for that we need to generate the keys for each party. Then after that, we run a BLS signature scheme on the first randomness. So we kind of assume there is a first randomness. Then you sign it, and then the signed value is random in the eye of adversary, because if it's not random, you can break the signature. So then you sign the previous random value again, and you have a new random, which looks random at the eyes of the adversary. As you can see, I can chain my randomness together. Without creating a new randomness, I can have a random value. And a very interesting property of BLS signature groups or threshold groups is that when you sign a message, it's a unique message. The signature is unique. So for every message, there is only one signature that verifies. So if I sign a message, everybody agrees on the next randomness. So, and I only know BLS threshold groups who have this property. They call it uniqueness property. And another interesting property of the BLS threshold signature is that they are non-interactive. So it means that when you want to sign, you don't need to connect to any other node in the system. You sign your own value, and then you send it to everybody, and that's it. So we don't have an O of n squared message passing. It's very, very cheap operation. OK, so now this is how we create randomness. And then we have a blockchain protocol that doesn't need to use proof of work at all. And it scales to a large number of parties. But still, I didn't tell you how we reach instant finality and how we can reach instant finality. Because I said we want to reach instant finality. We want to make sure if we reach agreement, we really reach agreement. So as I said, it's impossible to kind of check if we reach agreement among everybody, because it's a large group. But what we can do is to limit the redundancy, because we said that there are like 5,000 nodes who participate in the protocol. Not everybody needs to check if they reach agreement or not. We can create a random committee among everybody, and this random committee reach agreement and send the result to everybody. And that's enough. Why it is enough? It's like a parliament. You don't need, not everybody needs to participate in the voting process of this new rule. As long as you know that a group is like well-defined and a group can participate in that procedure, it's enough. So we delegate the job to the committee instead of doing the job. Everybody participate in doing the job. So it has other properties. For example, it gives us parallelism other than being scalable and have instant finalities. We can scale, and we need a smaller communication and computation cost. Yes?
Sort of the last election showed with our elections.
Yes. It's a different election. It's a random election. They don't.
But you can, let's pretend you wound up having people inside here, guys that communicated those were some bad generals, for example.
Yes. Exactly. I'm going to talk about why in a random selection. Sorry? Oh, sure. The question was, election is not the best method of choosing honest groups, because sometimes election fails, and the members of the group can be dishonest or adversarial, and then if the whole committee has larger than 2/3 adversarial nodes, then they can break the safety of the protocol. And the answer is yes, that's correct. So we use a random selection method, which I believe is the best way of selecting in a way that we can guarantee the number of bad.
So your point is it can still fail, but at least it's the best. This is the best.
It can fail, but we bound the possibility of the failure. I show you how we bound the possibility of failure. It's a probabilistic protocol that still can fail, but the probability of failure is very small. So it's like this. So assume we start with a universe that 20% of the parties are adversarial. Now, if I sample a random group using my previous randomness, I can sample a random group of a smaller size, of like 100, 200 size. then the possibility that 30% of them are adversarial is very, very small, or more than 30% of them are adversarial is very, very small. It's because if you have a group and sample from them, the nature of the group doesn't change that much if the sampling is complete random sampling. So that's how we kind of can solve this specific problem that was asked. So then that's it. So that's the whole protocol of Dfinity. We know how to create randomness. We know how to reuse the randomness. And now we know how to sample a small committee to reach finality faster for us and reach instant finality. So they know when they reach finality, they can tell everybody else, oh, this round was good, we reached finality. So everybody else can know. And so what we learned is that unique threshold signatures are very well tool for randomness. And use committees. They are very cool tool to reach scalability. If you have a large data, if you have a large number of nodes, committee-based protocols can really help you to scale to large settings. Yes?
When you say large, what is that?
So it's like around 5,000 nodes to 10,000 nodes currently. It can scale to more than 15,000 nodes as well. But that's the limit we tested so far. OK, thanks so much for your patience. And so,
go through this decision-making process n times where n is very large. How often do you potentially have decisions that are made which are wrong? And
Okay.
You say it's rare, but how rare
yes.
is rare?
So it depends on the size of the committee that you choose. For a roughly 300 committee, we calculated the probability, and it's around 200 years. So after 200 years, you might reach a decision that is not safe anymore. And we assumed we choose committee every 5 seconds. We choose a new committee every 5 seconds, and then it took around 200 years. So it's very large. So the probability is very small. You can calculate the probability using hypergeometric methods in mathematics, or there are other methods that you can estimate the probability. If you read our paper, the Dfinity paper, we had those calculations there.
I'm just looking for simple assumptions. What percentage of bad actors did you assume sometimes?
Oh, so the percentage is that we went from 1/3 of adversarial nodes in total population to 1/2 of the adversarial nodes in committees, and we used a synchronous setting. We also have calculation for 1/4 to 1/3. It's not that bad. Okay.
You said it's scaling to 10 to 15,000 nodes on the test network. Dominic Williams talked about designing a system for 1 million computers essentially. How's that look?
Oh, sorry. I was going to say 5 million to 10 million. It was my mistake. He's right.
Oh.
Sorry. I apologize.
You had a slide on sharding that you skipped over.
Yes. I thought that you guys asked questions, so I thought I don't have enough time to talk about sharding. So community-based protocols give you sharding.
You could do that.
Sure. So instead of doing the computation as a full replica like Bitcoin, because Bitcoin is a full replica computation, that's like all the nodes do the computation that is the same for everybody. Instead of doing that, we can have each committee to perform a computation that is unique to that committee. And then after we have multiple committees, like they can agree on different things in parallel, and we can get sharding from there, which is a short answer.
So in the Bitcoin, there's some financial incentives to basically add on to the chain so that the previous blocks are corrected and only extend to the valid chain. So
Yes, that's the beauty of blockchain. You can only extend them.
But in this protocol, what are the incentives to extend, to continue extending along with it, correct?
So in these protocols, the nodes are like ISPs. So they have to be joined to the Dfinity protocol, and if they participate in the creating randomness, being a leader, they receive some money from the whole protocol, because like users use the protocol, they pay for the computation that they are doing. So their incentive is also monetary incentive.
Any more questions?
Has the consensus protocol changed at all since the white paper came out? Or if I read that, will that still be updated?
It changed a little bit, yes. We are now in an asynchronous setting instead of synchronous setting, and we changed some part for efficiency. The general idea, the concept that I introduced here is the same, but the details obviously change every day, so it's a ongoing research.
I think we can take 2 more questions.
I'm just trying to make sure I've got this right. The reason why it's so rare is that all the committee members must agree on the decision for the decision to be agreed.
No, the threshold of them.
It's a threshold. So if it's a threshold, and if there's a large percentage of bad actors, then wouldn't it be the case that sometimes you'd have a committee composed largely of bad actors, and why couldn't they then?
Yes, but we set the parameters in a way that that event happened in a very, very small probability. So the probability of that event happen is 1 over 3 to around like the number of committee members. So a very, very simple math is that assume I have a population that is infinite. So every time I choose a node, I know that with probability 1/3, he's dishonest. So then if I choose 300 nodes, then the probability that all 100 of them are dishonest is 1/3 over to 100. So if you want to reach that event, you should repeat 1 over that probability, which is, this was a really long time. It's not a complete correct analysis. It's a very envelope, yes, back of the envelope rough analysis. For a detailed analysis, you have to do hypergeometric analysis.
Okay, but still probabilistic decision.
Yes, it is still a probabilistic decision.
Thank you again to Mahnush for taking the time and being here.